We've spent a lot of time talking about finding solutions to second-order homogeneous differential equations, second-order linear homogeneous differential equations. Let's talk now about what to do if we have a non-homogeneous linear differential equation. So remember, we have this linear operator L of y, which for a second-order linear operator would be y double prime plus p of t y prime plus q of t times y. A general second-order linear non-homogeneous differential equation can be written as L of y equals g of t. Remember, this is exactly the same as just writing y double prime plus p of t y prime plus q of t y equals g of t. This is the differential equation we would like to solve. We'll talk about, for a differential equation like this, we'll talk about the corresponding homogeneous equation as just what we get if we replace g of t by 0. That's the equation L of y equals 0. Now, we already know from the general theory that the general solution to the homogeneous equation is just y equals c1 y1 plus c2 y2, where c1 and c2 are any real numbers. And of course, we need y1 and y2 to be a fundamental set of solutions to the homogeneous equation. In other words, the Wronskian must not be 0. Now, my claim is the general solution to the non-homogeneous differential equation is very similar. You just take the general solution to the homogeneous differential equation, c1y1 plus c2y2. Again, c1 and c2 are just arbitrary real numbers, and y1 and y2 are a fundamental set of solutions to the homogeneous equation L of y equals 0. And what is capital Y of t here? We can use for capital Y of t any particular solution to the non-homogeneous equation L of y equals g of t. So that's this equation here. This equation is exactly L of y equals g of t. So what do we need to do? If we want the general solution to the non-homogeneous equation, I claim we just need to find one solution somehow. We haven't talked yet about how. That's what we'll be doing right away. But somehow we need to find one solution to the non-homogeneous equation. And then I claim all the other solutions to the non-homogeneous equation just look like that one, plus some solution to the homogeneous equation. Why is this true? Why does this work? Well, if I have two solutions, and let me give them names, I'll call them phi1 and phi2. If these are two solutions to the non-homogeneous equation, L of y equals g of t, what can we say about their difference? Well, L of phi1 minus phi2, by linearity of this linear operator L, will just be L of phi1 minus L of phi2. But of course, saying they're solutions to this equation means L of phi1 is g of t, L of phi2 is g of t. So we get 0. In other words, phi1 minus phi2, phi1 minus phi2 is a solution to L of y equals 0, the homogeneous equation. That's an important thing. If you have any two solutions to your non-homogeneous equation, and this is for linear differential equations. We're talking here about second order linear differential equations, but this will actually apply to any order linear differential equation. Then the difference has to be a solution to the homogeneous equation. In other words, another way to write this is that the second function, phi2, since phi1 minus phi2 has to be a solution, phi2 just has to be phi1 plus what I'll call y sub h, where this is some solution to the homogeneous equation. And that's really all we're saying here, because if we think of phi1 as our capital Y, and phi2 is just any other arbitrary solution, so just I'll call phi2 y here, I'll call phi1 capital Y. All of my solutions, little y, have to look like this one solution, phi1, plus some solution to the homogeneous equation. Well, this is the general form for all solutions to the homogeneous equation, c1 y1 plus c2 y2.